Hello, Linear Algebra students, Math 2331. In this video, we are starting to prepare for our final exam. We are going to go over 30 true-false questions that can really come from any part of the semester. The questions are structured in that the first 18 come from previous midterms of mine and more or less are chronological. And then we will have two sets of 6, which are off recent final exams and could come from any part of the semester. The one thing I will say, quite often, no justification is needed for students. However, I'm going to talk about why all of these questions are, well, either true or false. So we get started. Number 1, there exists a 3 by 3 diagonal matrix A with A times this 1, 2, 3 equals 4, 5, 6. This is true. And we can create such an A, just to think about this. If we think linear combination of columns, what I need is 1 times the first column of A plus 2 times the second column of A plus 3 times the third column of A to be this. So what can we do? We can make 4, 0, 0. We can make 0, 5 over 2, 0. And finally, we can make 0, 0, 2. This is certainly diagonal, and if you multiply by 1, 2, 3, you can verify. We get 4, 5, 6, which is exactly what we wanted here. Okay, next question. The matrix, well, here we have 2 rows and 6 columns is in row echelon form. If this said reduced, this would be false. However, you see, this is true because what do we have? Here's, say, pivot position, leading entry, and leading entry. And, well, the first non-zero entry in each row is something, and every row above has a leading entry and to the left. So this is in row echelon form, but not reduced. Wonderful. There exists a 2 by 3 matrix A and a 3 by 4 matrix B, such that the product AB has rank 3. Well, we can think about the size, A times B. If A is 2 by 3 and B is 3 by 4, certainly we can make the product, but you notice that AB is 2 by 4. Now, can we have a 2 by 4 matrix with rank 3? No. So this cannot have rank 3 because we only have 2 rows. It's not enough rows to have a leading 1 in every row of its reduced row echelon form. So this is a false question. Number 4, if A and B are invertible n by n matrices, then the linear system AB times X equals 0 has a unique solution. Sure, this is true. Well, the product of invertible matrices is invertible. That's one way to think about it, but also we could just multiply. So if you want to solve ABX equals 0, we can multiply both sides by A inverse. We would have BX is A inverse of 0, which is 0. And now multiply both sides by B inverse. So you would have X is B inverse, which is 0. Here's our unique solution. So that's one way to think about it. Also, as I mentioned, the product of invertible matrices is invertible, but this is true. Number 5, suppose A, B, C are 2 by 2 matrices. A commutes with B, B commutes with C. Then A commutes with C. Well, this is a false statement. Let's take B to be a matrix that commutes with everything. For example, let's let B be the 0 matrix. A and C be some 2 by 2 matrices that do not commute. Okay, so maybe we can do 2, 1, 0, 0, and then we'll let C be the matrix of all 1s. We can calculate AC, calculate CA, and these will not be equal. We will see. Okay. Well, AC, we have, when we do row dotted with each column, we have a 2, 2, and then here will be 1, 1. Now CA, if you take matrix times the first column, you just get 2 times the first column, which is 2, 2. Takes matrix times the second column, you get 1 times the second column of C, which is 1, 1. So this is an example, and I could make a remark that B commutes with, well, in particular, both A and C. It means with every 2 by 2 matrix. So this is an example justifying that 5 is false. Number 6, the 2 by 2 rotation matrix. Here, this is rotation counterclockwise by angle theta. Well, this is an orthogonal matrix. This is true. You can think about this multiple ways. You can either think that the associated action is definitely length preserving. Take a vector, rotate it counterclockwise. You have not changed the length. But also, you could just think about this as a matrix. We notice that the columns are, what do we need? Well, we need orthonormal. They are unit and perpendicular. Maybe I will just say this. So this is enough. As I mentioned, you could also think about the geometric action. Okay, next page. Number 7, V, W, X are in Rn. If this equation holds, then the set must be linearly dependent. This is true. All we need to do is move everything to one side. So if I do that, we would have 3V, we would have 6W, and then we would have 10x equals 0. Well, you see, this is a non-trivial linear relation, and this would say that the vectors are linearly dependent. Number 8, there exists a linear transformation T from R2 to R5 such that the dimension of the image of T is 2. This is going to be true as well. How can we think about this? Well, the associated matrix, we can take the associated matrix A will be, we take in something from R2 and we give out something in R5. You take A to be any 5 by 2 rank 2 matrix. This will work because the dimension of the image of T is the rank of the matrix. And certainly we can have a 5 by 2 rank 2 matrix. Number 9, is this set an orthonormal basis for R3? We have to be careful about this word. Basis for R3, sure. Orthonormal basis for R3, no, it is not. So this is false. The reason, well, we just take one of these. If you take the length of this vector, 3 minus 1, 0, this is a square root of 10, which is not equal to 1. Orthonormal means unit and perpendicular. This is an orthogonal basis for R3, but not orthonormal. Similarly, this vector has length square root of 10. Okay, number 10, there exists an orthogonal transformation T from R3 to R3 such that T of 3E1 is 2, 1, 2, and T of E2 is 1, 0, minus 1. We know orthogonal transformations preserve dot product, preserve length, preserve angle between two vectors. Now here, you notice this vector and this vector are perpendicular. Well, this vector and this vector are also perpendicular. You've noticed this vector has like length 3, and T of that also has length 3. But even though so far it's okay, the answer is false, because I'll write it this way. E2 has length 1, but T of E2 has length, well, we can see the length of what this vector is. It's the square root of 2. And so there is no length preserving transformation that maps E2 to this vector. Number 11, for any 5 by 6 matrix A, there is a non-zero vector in the kernel of A. Well, let's think about this here. We have 5 by 6, so we have 6 columns. Moreover, we only have 5 rows. So the rank of A is less than or equal to 5. We know the nullity of A. Well, we have 6 columns, so it is at least 1. So the answer is true. The dimension of the kernel of A, which is the nullity of A, is at least 1. So we will have a non-zero vector in the kernel of A. Number 12, for any n by n matrix A and the reduced row echelon form of A have the same determinant. Well, false, without a doubt. And we can give a counterexample that's just a 2 by 2. So what we want to do is pick a invertible 2 by 2 matrix that does not have determinant 1. Okay, let's just do this. This is invertible. We have 2 non-zero columns. The second is not a multiple of the first. We also see the determinant of A is 2, which would justify its invertibility. But the reduced row echelon form of A is the identity, and the determinant of the identity is 1. And so this is our counterexample here. Number 13, for any n by n matrix A and the reduced row echelon form of A have the same eigenvectors. Well, this is false. We can take, let's say we rotate by pi over 2 counterclockwise. This will be an invertible matrix. Okay, cosine, sine, minus sine, cosine. You can kind of see the characteristic polynomial is lambda squared plus 1. This has no real eigenvectors. However, this is an invertible matrix. The reduced row echelon form of A is the 2 by 2 identity, really any non-zero vector in R2 is an eigenvector for this matrix, but I will just say this has E1 and E2 as eigenvectors. So we can see from this example, it is definitely a false statement. Number 14, every matrix with this characteristic polynomial is diagonalizable. This is going to be false. It all depends, because we may not have enough linearly independent eigenvectors. I will just say it this way. Let's say A is diagonalizable if and only if the geometric multiplicity of eigenvalue 2 matches the algebraic multiplicity and the geometric multiplicity of eigenvalue 3 matches the algebraic multiplicity, and that certainly doesn't have to happen. Next question, every matrix, same characteristic polynomial, is invertible. This one is true because 0 is not an eigenvalue. So we will have invertibility. Number 16, if A is 2 by 2, determinant of A is not equal to 0, then A is similar to a diagonal matrix. Well, this part just says that A is diagonalizable. This is false. We can come up with an example like this, 2, 2, 1, 0. You see, this is not diagonalizable. This is not diagonalizable. We have only one eigenvalue. It's on the diagonal. And A minus 2i is this. We would need to have 2 linearly independent eigenvectors corresponding to lambda equals 2. And we do not. This does not have rank 0. Next question. 1, 1, 3 is an eigenvector for this matrix. This we can just multiply and find out. So we can take this matrix times this vector, see if we get a multiple of the vector. Okay, we have 2, 1, 1, 1, 2, 1, 1, 1, 2. We multiply by 1, 1, 3. What do we get? I have 2 plus 1 plus 3, which is 6. Next one, I have 1 plus 2 plus 3, which is 6. So far, it looks like it might be 6 times the vector, but let's see. Do this one. We have 1 plus 6, which is 8. Oh, the answer is no, false. That this 668 is not a multiple of 113. This is the last question that came off my midterms, and then we will have 2 sets of 6 from old final exams. If A and B are similar matrices, then A transpose and B transpose are similar matrices. This one is true. Let's justify. A and B similar, it means, so there is an invertible S with A equals S, B, S inverse. All right, how can we see that A transpose and B transpose are similar? Well, we can just take the transpose of this equation. So then A transpose will be S, B, S inverse transpose. Well, when you take the transpose of a product, it goes the other way. So this will be S inverse transpose, then B transpose, then S transpose. Now we have really one more step. S inverse transpose is S transpose inverse, then B transpose, S transpose. So you see, these two are related in that we have some invertible matrix, B transpose, that invertible matrix inverse, and that equals A transpose. The answer is true. Now, let's move on. This page has 6 true and false from the fall 2022 final exam. Well, letter A, the set of solutions of this linear system is a subspace of R3. This is false. The reason, well, for example, 0 is not a solution, and every subspace must contain 0. B, the eigenspace associated with an eigenvalue lambda of an n by n matrix A is a subspace of Rn. This one is true. An eigenspace, I'll write it as E sub lambda. This is a kernel of a matrix. So this is the kernel of A minus lambda I. And every kernel is a subspace. In fact, we proved that in class. Letter C, the set of vectors V in R4 such that V dotted with this vector is -2 is a subspace of R4. Well, this is false. Really for a similar reason as letter A is false. So maybe let me call this vector X. Then you notice that 0 dotted with X is 0, which is not equal to -2. And so 0 is not in this set. This would be a reason why C is false. Okay, next question. The function from R3 to R3 given by this formula is a linear transformation. This is true. Let's justify. Well, we can write down the matrix. What would we need to do to find the matrix of a transformation? In fact, this would justify we'd have a linear transformation. Evaluate at E1, we would have 1, 0, -1. That's the first column of the matrix. Evaluate at E2, we have -1, 1, 0. That's the second column of the matrix. Then we evaluate at E3. We have 0, -1, 1. Well, we have a matrix such that A, if I call this A times X is this formula. You can check. And so this justifies we have a linear transformation. Letter E. Now we have a function from R4 to R3. And here is the formula. The question is, well, the statement is this is a linear transformation, and then we decide true or false. This is false. And we will also see the last one will be false. Two different functions. We're trying to determine if they are linear transformations. Let's justify the first one. Well, what happens when I evaluate T of the 0 vector? We know if we have a linear transformation, T of 0 must be 0. In this case, T of 0 is -1, 2, 0, which is not equal to the 0 vector in R3. And this would say false. As I mentioned, letter F is also false. Well, if you've seen it, this function is a quadratic form, but we don't need that language to solve the question. So we could write down what this function is to help us figure this out. Okay, what is T of XYZ? Definitely it is a map from R3 to R. And if you multiply these three matrices, well, you're going to get x squared plus y squared plus z squared minus 2xz. I will let you check that for yourself. I'll put this in parentheses. Check this. If you are interested, you can check this. Now, when I see squares, or even this part, that is, my intuition says that is not a linear map. But if we actually wanted to justify, let's see. T of 0 is 0, so it's not the same reason as in E. But let's take T of 1, 0, 0. Here, I'll actually take time to write this out. We have 1, 0, 0. And then it's going to be times, well, if I take this matrix times 1, 0, 0, it's just the first column of the matrix. So we have 1, 0, -1. Now this is just 1. At this part, maybe I will delete this. This was just to give us intuition. So let's delete this. We can move this up. T of -1, 0, 0. If this is a linear transformation, this better be -1 from properties. Well, let's calculate. This would be -1, 0, 0. Now, take this matrix times -1, 0, 0. We get -1 times the first column of the matrix, which is -1, 0, 1. Now you see this is also +1. This is the issue, which is not equal to -1. And so the function T in letter F is not a linear transformation. Last page, we have 6 true-false that came from the fall 2019 final exam. A, B are n by n orthogonal matrices. The product is an orthogonal matrix. This is true. There's a number of ways you could justify this. Maybe I will do this thinking about length preserving. So let's figure out what is the length of ABX. Here x is some vector in Rn. Well, you see I could group it like this. Now, use that A as an orthogonal matrix. The length of A times BX will be just the length of BX, because A is an orthogonal matrix. The corresponding transformation is length preserving. Now, similarly, B is an orthogonal matrix. So the length of BX is the length of X. And this is for any X. In Rn. And this justifies, you see, we have ABX. Its length is the length of X. Wonderful. 2A, there is a 2 by 2 matrix A such that the kernel of A equals the image of A. Well, this one might be a little bit challenging to think about, but in fact, it is true. And let's create one. Not just dimensions equal, physically equal as subspaces. We can take this matrix A. It will be already in reduced row echelon form. So we can take 0, 1, 0, 0. You notice the image of A, the span of E1. On the other hand, if you try to solve for the kernel, you see it says x2 is 0, and then we have free variable x1. So this is also the kernel of A. Kind of a neat example. Letter B, there is a 3 by 3 matrix such that the kernel of B is the image of B. This one is not true. And how we can realize this is arguing with dimension. So we know that this is rank nullity here, the dimension of the image of B plus the dimension of the kernel of B must be the number of columns. Well, if they are equal, if the image of B equals the kernel of B, then we would have the 2 times. They have the same dimension because they're equal as subspaces. We would have, say, 2 times the dimension of the image of B equals 3. And this is not possible. You cannot have a dimension that is a fraction like 3/2. Dimensions must be integers. All right. Next question, we have 3 vectors in our 3. Are these 3 vectors a basis for our 3? The answer is true. We can justify a number of ways. Maybe I will do this as follows. If you take C1 times the first vector, this is pi 3, 5, plus C2 times the second vector, 2, 1.1, 0, plus C3 times the third vector, square root of 3, 0, 0. And this equals the 0 vector. So what we're trying to think about is, or justify, the only linear relation is the trivial relation. Well, we have 3 lines here. Line 3, we will start with, this says 5C1 is 0, and we get C1 is 0. We can march up. Line 2 would say 0 plus 1.1 C2 is 0. We get C2 is 0. Then march up one more line. Line 1, C1 and C2 are already 0. So we get 0 plus 0 plus the square root of 3. C3 equals 0. And we arrive at C3 equals 0. So this justifies the only linear relation is the trivial one. I have justified the set as linearly independent. And then I can just remark that 3 independent vectors in R3 form a basis for R3. Okay, wonderful. This one took a little bit more space than I had room for. Next question. The set, well, here's 4 vectors in R3, is linearly independent. Definitely not. So this is a false statement. There's a number of ways you could justify here. Maybe I will just use a rank, because this is a wonderful way to think about these types of questions. So if we put these vectors as columns, I have 1, 0, 0, 2, 3, 0, 4, 5, 6, and then 7, 8, 9. The rank of this matrix cannot be 4. We would need it to be the rank equal to the number of columns to have a linearly independent collection. And this matrix cannot have rank 4. It's only 3 rows. Here is the 6th true false on this page and the 30th true false in this video. Last one. A, B are n by n matrices. Then this equation holds. Well, let's see. We take A plus B times A minus B. What do we get? We have A squared. We have BA. There is a minus AB. And then minus B squared. Well, you see, there's the A squared minus B squared. But A and B may not commute. So the answer here is false. And the reason, well, A and B may not commute. If A and B do not commute, and we have seen many examples of this semester, then this will not be 0, and this equation would not hold. This is the end of 30 true false. Thank you so much, students.